A strange looking inequality here. We have a trigonometric left-hand side along with the square root of x here, and then it's the fourth root of this quadratic expression. Now it turns out this looks challenging, but it's really quite easy to prove this using the Cauchy Schwarz inequality. Now this inequality holds for all real valued sequences of a's and b's. And just to see how we can make this left-hand side fit, all we have to do is pop a 1 right here. Okay, and again, I have this lined up pretty well right here. A sub 1, B sub 1, A sub 2 right here. And let's go ahead and put the specter 1 in there. That's kind of useful. A lot of times there's something called the 1 trick where you can use it to make an inequality work out rather nicely. And the rest of this is pretty straightforward also. You see, this is just a straight handoff, A sub 1, A sub 2, B sub 1, B sub 2. And you can see this is, again, just a direct application, substituting everything into the right-hand side. Now notice this is a well-known result from trigonometry, the Pythagorean identity. Sine squared plus cosine squared is equal to 1 for all real numbers. All right, so we can just put a 1 right here. All right, so this whole part by a trigonometry result, it's just a restatement of the unit circle, melts to 1. And then right here, when you square the square root of x, you get x. And then this is the result. So this would be the answer to the question. We could write this as a problem and just put less than or equal to right here, and we'd be done with the video, okay? But we're supposed to actually somehow or other go from here to here, all right? Now, let's take a look at how that's gonna break out. I'm not even sure why I wrote that down. Oh yeah, I just recopied the result here, folks. So we've shown this much so far. We've shown this much so far, and how do we get it to this form right here? Well, the key observation here, which is just properties of exponents, is to note that if you have an object squared, and I'll just keep this symbolic because it makes it easier to see, it's basically just laws of exponents. So if you have, let's say, a quantity squared, in our case, the a would be x plus 1, right? And then you take the fourth root of that, okay, the fourth root. That's the same thing as saying a to the 2/4, okay? But a to the 2/4 is a to the 1/2, right? So this is equal to a to the 1/2. All right, and that's the same thing as the square root, right? A to the 1/2 means the square root of a. Okay, and of course that's the square root of a. And I'm just doing it symbolically here. Our a would be x plus 1 in this case. All right, so square root of a. Okay, kind of nice. Now that's why this all works, because if you'll note, x plus 1 quantity squared is x squared plus 2x. You see this 2 right here? When you square this out, you get x plus 1. X plus 1 quantity squared is x squared plus 2x plus 1. Notice that 13 over 12 is a little bit bigger than 1, right? And that explains how we went from a less than or equal to a strict. Okay, so this really completes the proof. We're done. We've shown that this is strictly less than this. Well, sorry. This would be equal to, I left it out. You can write this based on this reasoning right here. You can write this as the fourth root. I don't run out of room here. We can write that as the fourth root, okay, of x squared plus 2x plus 13 over 2. Let's lift that out. Plus 13 over 2 right here. Okay, folks, and that's it. And again, I hope this reasoning makes sense right here. This much is true. This is just equality right here. When you expand this out, you would get x squared plus 2x plus 1, not 13 over 12, but 13 over 12 is bigger than 1. That explains this. And so we just rewrote this. Since this is equal to all this all the way across, you can rewrite it in this fashion based on this property right here, okay? And the a squared right here, the a squared, this is a little bit bigger than the a squared because it's 13 over that should be a 12, right? 13 over 12, sorry. 13 over 12. Okay. All right, folks, I like that one. Hope you enjoyed it.